Welcome, gentlemen, to Aperture Rituals. Astronauts, war heroes, Olympians, you're here because of an ancient mating ritual etched in a monolith by the elder monks to forestall the end of days. So, who is ready to make love to a giant bird?
So I did my physics project on Portal. Portal, or more specifically Portal 2, is a physics puzzler game made by Valve that deals very heavily in manipulation of physics via portals. Quick explanation of portals as follows. You have two portals, one blue, one orange. You have two portals on two flat surfaces. You can't have them on rounded surfaces or black surfaces, and you can connect 2 points in space, which allows for easy travel between 2 points, like so. Now the way this usually works is like a displacement problem. Now, let's say I wanted to get from there to there, and we assume that this is, oh, I don't know, maybe 5 meters. You could walk all the way from the origin there and make your displacement match your distance, both being fine, or you could use a portal, and if this was the origin we needed to get there, put a portal there, move like that. Distance traveled is 1, displacement is 5. Here we have Cuban button. Pretty simple. Newton's third law states that for each action there must be an equal and opposite reaction. The button presses up on the, or pushes upward on the cube, but because of friction, the cube wins out and pushes the, or depresses the button. Now, as I'm sure you've noticed, the player character in this game moves at a pretty constant speed, doesn't accelerate. So if you wanted to accelerate or needed to accelerate to solve a puzzle, you would use this speed gel, which creates a frictionless surface, allowing for easy acceleration. Well, for as far as the coded surfaces, or for the distance of the surface that's coded. Now, what Portal really deals in often is projectile physics. Now we know that throw this over there. Now we know that when you launch a projectile, it forms an arc, like so, and that if you modify the height of that, or the height of where the projectile is being launched from, you get a different arc. Different arc, but same initial velocity, and only a slightly different distance. Delta x equaling velocity x times time, after all. And that when you launch something at a 90-degree angle, it goes up, stops accelerating, and accelerates downward at the speed of gravity, 9.8 meters per second squared. But what's really interesting about Portal is that, Portal and projectile physics anyway, is that portals do not affect momentum. Now, let's say that, well, here's a quick kinetic energy and potential energy problem, and a quick explanation of it. When you start, or before I move off this ledge, I have a given potential energy based on the height of this drop, which can be calculated by the equation PE equals m times g times h, mass times gravity times height. And as I fall, my potential energy rapidly changes to kinetic energy, found with the equation 1/2 of the mass of the object times the velocity squared equals kinetic energy. And we know from our studies that as we fall, as an object falls, its potential energy is converted to kinetic energy. Just about, it evens out right around the midpoint, and just before hitting the ground, there's no more potential energy, and it's all converted to kinetic energy. But with portals, you can prolong the fall and maximize the use of your kinetic energy, allowing for something like this. turning yourself into a projectile that can be flung far farther than the spheres and cubes and turrets that we just used. Now, to continue this project explanation, we need to get over here, which requires getting up onto that ledge, and to figure out how we can do that, we can use a trigonometry problem. Now, what we have here are a 45-degree angle slope and a 30-degree angle slope. Now, we know that to launch from 45-degree angles, you're launching for the maximum distance. So we can try this, but as it turns out, we don't have the correct vertical displacement to reach top of the slope. We can try it again at a 30-degree angle with the same velocity. But as it turns out, we get the height, but not the distance. Now we could just sit here and give up, or we could change our initial velocity by launching ourselves from a higher point and accelerating, which will in fact get us the distance we need. You can find the horizontal and vertical displacement using the equations r cosine theta equals horizontal, or r sine theta equals the vertical. And before we solve this little mock test and finish up here, I'm going to explain how, or I'm just going to note that Portal accurately portrays freefall, in that after a point you stop accelerating and go into freefall. Now, to solve this test, we need to get from here to that button there, which requires accelerating off of this ramp and launching ourselves, much like you would in any one of the numerous airplane travel problems we've done. But the problem is we can't run off of this, since we move at a constant speed and we don't accelerate quickly enough to be able to ramp off the ledge and take flight, more or less. But what we can do is use the speed gel to accelerate ourselves. Basically what's going to happen next, because this is going to go by kind of fast, is we're going to travel over this distance to change our final velocity. Our initial velocity is of course 0, since we're starting at rest, to accelerate over the length of the runway, giving us the speed we need to make it here. This one's a little far-fetched, since we don't have the levitation. We don't have tech for this yet, but essentially this could be called a net force problem, in a sense. And roughly, that is this portal. We're done here.